So they fly you down on a military cargo plane, so it's not like your passenger jet with windows everywhere that you can kind of see where you're coming into. And you just kind of land and they tell you you've arrived on Antarctica and pop open a door.
Thank you.
No worries, see ya.
It's really breathtaking the first time you walk off the plane. You get a blast of cold air in the face and it's sunny. Everything's white, so it's really bright and sunny. So we landed in McMurdo, which is on the coast, so you've got this huge volcano in the background, Mount Erebus, and the Transantarctic Mountains and Mount Discovery off to one side, and sea ice and a little ice shelf that you've just landed on. I think the thing that struck out to me the most was you have these small little stations and you can easily get in your head that you're on campus or wherever, but sort of realizing that when you look out that it's like, yeah, the next place is a couple thousand miles of nothing, just white snow. It's a long way from home.
It took us about 12 days to conduct the entire traverse from South Pole back around to South Pole. And that's moving, roughly 7 or so hours a day of travel. And then the real work begins. What we're doing is collecting GPS data, which gives us not only our latitude and longitude, but it also gives us our elevation. We take those GPS elevation measurements, which are precise down to about the centimeter level, and we compare them directly against ICESat-2's elevation measurements. We go to this part of the world because basically the ICESat-2 orbits all converge at 88 degrees north and 88 degrees south. So we get the densest data record. That's great from a validation standpoint. Antarctica is a great place for this type of validation. It's a relatively unchanging surface at that latitude and at that elevation. I mean, we're interested in the centimeter level accuracy of the satellite and centimeter level accuracy of our GPS data. The reason why we're interested in that is imagine a centimeter of water over the continental United States and now putting that into the ocean. That's obviously a lot of water. Ultimately, when we're interested in that level of change over that great distance, those centimeters become really, really important.
It's amazing how much elevation changes the environment. The air's drier, it's colder, the wind bites a little harder.
What you doing, Kelly?
Closing up the GPS. Trying to breathe.
Trying to breathe? What's the problem with your breathing?
We're at 10,000 feet above sea level. Getting higher every day, it seems.
One of the additional instruments that we brought this year was this downward-looking laser to get a grip on surface roughness as we're driving along, sort of small scale sastrugi and rolls in the snow as we're driving along. And that gives us a handle of how much the GPS is moving around, if it's floating on top of the snow, if it's moving with the roughness of the surface, and then ultimately make corrections for that if we need to.
We've had 2 amazing traverses. The first one was fantastic and a bit pioneering and figured out what worked, what didn't work. Second one improved on that. We've already thought about ways that we're going to improve the next one for sure. Maybe streamline things, make things a little bit lighter. It's only getting better and better.